Hello classmates and professor, my name is Rebecca Figueredo and today I will be teaching you about quaternions. In our lesson, I will be providing an example of quaternions as well as the properties used in order to solve our example. Now, before we get on to the example, I want to provide a clear definition of what quaternions are. A quaternion is a system of numbers that extends complex numbers. It is in the form of a1 plus bi plus cj plus dk, where a, b, c, d are real numbers and I, j, k satisfy the following condition. These are also known as Hamilton's rules, and I have included it in this lesson so that we can refer back to it when we do the example. Ij and negative ji equals k, jk and negative kj equals I, ki and negative ik equals j. Additionally, I to the second, j to the second, k to the second, and ijk are all equal to negative 1. Now, our example states, show whether quaternions under multiplication are commutative. And we know how to show commutativity simply by showing that a times b equals b times a. Now, suppose we have the following. A equals u, which equals 2 plus 3i plus 4j, which is our quaternion, and b equals v equals 4i minus 3j minus 2k. We'll take a second to note that these two quaternions only have 3 terms, or there's only 3 terms written, but in our definition we have 4. So what is happening here? Technically we do have 4 terms written here, and it is in the form of a quaternion. Now we have 2 plus 3i plus 4j. What we don't see is that we don't see our k, which is actually equal to 0k, where our d is a real number of 0. And 0 times k is simply 0. That is why we only see 3 terms, when there's actually 4. In our second quaternion, we are missing our a1, where in this case our real number, or our a would be the real number 0, which would be 0 times 1, which is simply 0. And we would follow it by 4i minus 3j minus 2k. So for these two quaternions, we see 3 terms, but there's actually 4, with those being real numbers of 0. Now, we would substitute u and v into our given property, a times b equals b times a. We would get the following. U times v equals 2 plus 3i plus 4j times 4i minus 3j minus 2k. Here's where we include the distributive property. We would take each term, 2 times 4i, 2 times negative 3j, and 2 times negative 2k. Additionally, we would do the same thing for 3i and 4j, and we would multiply times 4i minus 3j minus 2k. 2 times 4i equals 8i, 2 times negative 3j equals negative 6j, and 2 times negative 2k equals negative 4k. And if I scroll down, you can see that I've done the computation for us. We end up having 8i minus 6j minus 4k, which was the first one I did, plus 12i to the second, because 3i times 4i equals 12i to the second, negative 9ij, negative 6ik, plus 16j minus 12j to the second, minus 8jk. And when you distribute, make sure that you keep the first term, in this case I, the first letter you write, because if you were to have written it as ji, it would have changed the equation altogether. Now, some of these are highlighted. Why? Because we'll be referring back to our Hamilton rule. Notice that we have an I to the second and a j to the second, and we know that I to the second, j to the second are equal to negative 1. So we would have the following. Negative 12, because we would substitute that negative 1 for our I to the second, and negative 1 times 12 would be negative 12. Ij is also on here. Ij equals k. So if ij equals k, we would substitute that and we would end up with negative 9k. Ik is another one we have. And notice that we already have negative ik. So we would end up having plus 6j. Ji is another one. So ji is equal to k. But notice that we're missing a negative. So it would be negative 16k. Then we have j to the second, which I said before is equal to -1. So negative times negative is actually positive, so we would have a positive 12. And our last one is negative 8jk. jk is also one of our Hamilton rules. It is right here. jk equals I, so we would be left with negative 8i. If we scroll down, you can see it written out better, where we have 8i minus 6j minus 4k, negative 12, which we mentioned, negative 9k, which we mentioned, plus 6j minus 16k, plus 12 minus 8i. From here, we would then combine like terms, find the ones that are similar, and put them together. So we notice that negative 8i and 8i are the same. We have negative 12 and positive 12. We have negative 6j and positive 6j. And we have 3k's, negative 4k, negative 9k, and negative 16k. After combining like terms, we end up with negative 12 plus 12, which we notice they cancel, and we're left with 0. We also have 8 minus 8, which also cancel, equals 0, and 0 times I equals 0. Negative 6 plus 6 also equals 0, and 0 times j is equal to 0. Our last numbers are negative 4 minus 9 minus 16, which simply equals to negative 29k. So we end up with simply one term, negative 29k, my apologies, and the rest being 0. So that means that when we do v times u, we should only get negative 29k for it to be commutative. However, if we do not get negative 29k when we do v times u, then we have proven that quaternions under multiplication are not commutative. So let's see what happens. Now we would show b times a, which we would substitute v and u, which would be v times u. So now we have 4i minus 3j minus 2k being our first term, and 2 plus 3i plus 4j. We would still do the distributive property and do 4 times i times 4i times 3i times 4i times 4j. 4i times 2 is 8i. 4i times 3i equals 12i to the second. 4i times 4j is 16ij. We would continue doing the distributive property and get the following. As we mentioned before, we did the first 3. Then we would get negative 6j minus 9ji minus 12j to the second minus 4k minus 6ki minus 8kj. Now again, notice that some of these are highlighted simply because they are our Hamilton rules. And if we have written it down earlier and are aware of the Hamilton rule, we know that I to the second is negative 1, so we would have negative 12i. That 8 stays. Then we would have ij. Ij is equal to k, so we would have 16k. This one would stay, so we would have negative 6j. Our ji is equal to k, and notice we have the negative, so it's positive 9k. Our j to the second is just negative 1, and negative times negative is positive, so we have positive 12. Our negative 4k stays, so we bring it down. Ki is another one of Hamilton's rules, which simply gives us j, so we would have negative 6j. And finally, kj is again a Hamilton rule. We have that negative, so we would end up with positive 8i. And if this is messy or unclear, I've written it again. So here are the numbers we just did. And from here, we could then combine like terms once more. We have 8i and 8i. We have negative 12 and positive 12. We have, again, 3 terms for our k. And finally, we have negative 6j and negative 6j. So when we combine like terms, we end up having negative 12 plus 12 cancel again. However, a plus 8 is 16i. Simply just by doing the first term, we know that it's not going to be the same as u times v that we did earlier. But let me continue. Negative 6 and negative 6 equals negative 12j. And negative 4 plus 9 plus 16 is all equal to plus 21k. Notice here we have three terms, and if I scroll down, we can see it clearer. Notice that u times v equals negative 29k, and v times u is 69 minus 12j plus 21k, which are not equal, and therefore quaternions under multiplication are not commutative, simply because the following numbers that we got in our terms are not equal to each other, and therefore a times b is not equal to b times a. And therefore we have shown that, quaternions under multiplication are not commutative. And the properties that we used in order to solve this are quaternions under multiplication not commutative, distributive property and combining like terms, and we've also used a bit of Hamilton's rules by substitution. Additionally, I've provided the properties of, let's say, this quaternion times this quaternion and all the given properties, and we would do x1 times x2 and x2 times x1. And I've also shown here that they are not equal to each other, even if we have another form of quaternions being multiplied with each other. And that brings me to the end of my presentation that demonstrated that quaternions under multiplication are not commutative. I also have my references for information that I use as far as properties goes, and demonstrating again that quaternions aren't commutative. But yes, that is the end of my presentation. I hope that you've learned something new, and take care. Have a wonderful day.